Hello, my name is Kurt Gonter. I'm a thermal engineer in the Spacecraft Mechanical Engineering Group at the Johns Hopkins Applied Physics Laboratory. Intimately linked to illumination is the thermal environment of the Moon. The lunar surface is characterized by a complex and extreme thermal environment. There is a wide range of global lunar minimum and maximum regolith temperatures, as these values are sensitive to the varied surface topography across the Moon and regolith thermophysical properties. Since 2009, the solar reflectance and infrared emission of the Moon have been measured by the Diviner Lunar Radiometer experiment on board the Lunar Reconnaissance Orbiter. The data collected has been used to generate numerous global lunar surface temperature maps at different times, such as those shown here for both local noon and midnight. Diviner observations evidence temperature decreases with latitude and local time more drastically at the polar regions. For example, at the equator, the mean temperature is about 216 Kelvin. However, temperatures between noon and midnight at the equator vary by almost 300 Kelvin and can change drastically within 1 hour of sunrise or sunset. At the lunar poles, the mean surface temperature is approximately 104 Kelvin, with an average maximum of 202 Kelvin and minimum of 50 Kelvin. But how do these extreme temperatures and shock-like changes affect lunar system components? A recent measurement of hardware temperatures on the lunar surface was completed by the Chang'e 4 lander, which landed on the far side of the Moon, on the eastern floor of the von Karman crater. Several temperature sensors were placed at different locations on the lander, denoted in the images on the left and listed in the table shown on this slide. One significant difference can be seen for the minimum temperature measured. For the sensors on the rover transfer mechanism, the recorded temperature was as low as 78 Kelvin, or minus 195 degrees centigrade. This was due to their contact to the lunar soil and the shadows induced by the transfer mechanism and lander. In contrast, those sensors on the side panel, cushion mechanism, and footpad stayed warmer, particularly the footpad sensor, which was not affected by shading. This recent case evidences the need to consider and understand the thermophysical properties of hardware and regolith, as well as the conditions that can lead to extreme temperatures, such as illumination. Consider, for example, an object that has landed on the lunar surface. As shown in the image on the right, hardware and lunar surface temperatures are a consequence of direct incident sunlight, reflected sunlight, conduction to and from the object, subsurface heat flow, and view factors to space. Time of day, site geomorphology, and local topography also play a role in establishing the heat balance for a given system. As such, lunar thermal analysis must consider all radiative components of the energy exchanged between this object and the lunar surface, conduction between the object and the surface, and material properties for both. One of the most difficult scenarios for lunar system operation is the absence of sunlight or a naturally occurring heat source, such as during the lunar night. For this reason, many missions continue to be constrained in both duration and landing time of day. Alternatively, if hardware is designed for both sunlit and shadowed conditions, it could be exposed to a very large temperature range that includes cryogenic temperatures. Timescales are also a factor, as hardware temperatures can change in a shock-like fashion. Many common engineering materials are not rated for these extreme temperatures or rapid changes, both of which demand extensive ground-based testing and characterization. An example is shown on the bottom right for carbon fiber and polymer matrix composites targeted for cryogenic fuel tanks. Mechanical loading in a cryogenic environment reveals a high chance of delamination and propellant leakage due to microcrack formation. Ground-based testing can also be limited by the availability of chambers capable of exposing hardware to the wide thermal vacuum ranges. Detailed thermal modeling and analysis can help reduce uncertainties in a given system's expected temperature range. Common software tools used for this purpose include Thermal Desktop, Thermal Moon Simulator, and standalone MATLAB codes. For a system based on the lunar surface, regolith thermophysical parameters are necessary and can be found in literature. Some of those resources will be discussed in the regolith section of this module. Other references include the Human Landing System Lunar Thermal Analysis Guidebook, which provides conservative hot and cold boundary conditions for on-orbit and landed spacecraft. Whether the system is targeted for lunar day or night operation, lunar system designs must incorporate thermal management hardware. Dust-tolerant radiators and optical solar reflectors are some examples of common thermal control components, along with MLI blankets, with constructions common to orbiters. Other more complex thermal technologies, such as advanced thermal storage, heat switches, and variable heat rejection radiators, are active research areas envisioned for lunar night survival. Finally, thermal engineers must consider thermal vacuum testing as an integral part of system integration and test campaigns. In practice, these thermal vacuum tests are conservative, applying margins to both hot and cold operational and survival temperatures, as well as a factor of 3 or more for lifetime thermal cycles. The particular thermal chamber used during system testing must be appropriate for a given lunar mission environment, as many thermal vacuum chambers are limited in size and achievable soak temperatures, especially on the cold side. Some thermal vacuum chambers also incorporate regolith simulant, which can be essential for some testing applications. A list of test facilities is available on the LSIC Confluence page, as well as on the Lunar Engineering 101 resources page. But be aware that chamber cost and availability are intimately linked to the size and complexity of the test. Thanks for watching, and I hope this module has been informative.